So in the previous lecture, I have mentioned that the instantaneous power in a three-phase system is a constant value. Okay. So that is one of the advantages of a three-phase system. So we will now see why that is the case. So three-phase power. For this, you consider a star-connected load. So here we are considering the impedance, not a three-phase source. So this we can take as A, this is B, and this is C. Okay. What will be this point? It is the neutral. Now here we are taking a balanced load. So in case of a balanced load, what will happen to the magnitude and the phase? The magnitude and the phase of each of the impedances should be equal. So this you can take as Z angle theta, and here Z angle theta. Okay. Now the voltages, if you are taking as this voltage, phase voltage is VAN, this phase voltage is VBN, and this phase voltage is VCN. Now these voltages we will represent in the time domain, not the phasor domain but the time domain. So why that is the case? Because we want to find out the instantaneous power here, right? So we will represent in the time domain. So VAN you can write as VM. VM is some maximum value of the voltage. So it will be Vm cos omega t. Then what will be VBN? This will be Vm. This will be lagging by 120 degrees, right? So omega t minus 120 degrees. Similarly, VCN, what will it be? Vm cos omega t plus 120 degrees. Next, we need the currents. So the current, the phase current and the line current is going to be same. Now the line current or the phase current, it will be flowing into the load, right? For the source, when we have taken star configuration, this current was coming out of the lines because that was the source. But now we are considering the load. So current is being delivered to the load. So what will be this current? This will be IA, IB and IC. So remember, we are taking the small values here to represent the time domain. Here this voltage is also you can represent with the smaller letters. So that will avoid unnecessary confusion. Okay. Here also use the small letter. Okay. Now what will be the expressions for current? IA you can write as some maximum value cos of omega t, and what will be the phase? See here the impedance is Z angle theta. So when an impedance angle is theta, how much will the phase be? How much will be the phase of the current? Right? So it is going to be lagging the voltage by this theta degrees. Right? So here you can write minus theta. If theta is positive, that it is a capacitive load, then theta, IA will automatically come as a leading load. Okay. So for now, if you know that the angle is theta, then the phase of IA will be minus theta. Okay. So that's why we are writing here IA is equal to Im cos omega t minus theta. Then what will be IB? This will be Im cos omega t minus theta minus 120 degrees. It will be lagging the current IA by 120 degrees. And IC is going to be Im cos omega t minus theta plus 120 degrees. Now what will be the instantaneous power? P of t, the three-phase instantaneous power. Remember. Okay. So this is going to be for all the three phases. So what is it? VAN, that is the voltage across the phase A load, into the current through the phase A load is what? IA. Similarly, through phase B, VBN into IB plus VCN into IC. So what will you get here? VM cos omega t into Im cos omega t minus theta. Okay. Similarly, for others you can write. Okay. So what will be the expression here? Vm Im will be common in all of the terms, and the rest of the terms will be cos omega t minus theta plus cos omega t minus 120 degrees into cos omega t minus theta minus 120 degrees plus cos omega t plus 120 degrees into cos omega t minus theta plus 120 degrees. Here we'll make use of a trigonometric expression cos A cos B we can write as 1 by 2 cos A plus B plus cos A minus B, right? This you can apply for each of these expressions here, right? So here if you take cos omega t minus theta, what will you get here? This is equal to Vm Im is anyways outside, cos A cos B, omega t is A, omega t minus theta is B. So what will you get? Cos 2 omega t minus theta plus cos theta. Similarly, the next term cos omega t minus 120 cos omega t minus theta minus 120. Okay. So there also you will get a 1 by 2 term. So 1 by 2 you can take common. So what will you get here? Cos 2 omega t minus theta minus 240 degrees plus cos theta once again. Okay. And the final term you will get cos 2 omega t minus theta plus 240 degrees plus cos theta. Now these three terms, if you see here, these form a three-phase balanced system, right? You can see cos 2 omega t minus theta. The next one is cos 2 omega t minus theta minus 240 degrees you can write as what? Plus 120 degrees. And finally cos 2 omega t minus theta plus 240 you can write as minus 120 degrees. So you can see that these are balanced three-phase system. This phasor is leading this by 120 and this phasor is lagging this by 120 degrees. Okay. So if you add three of them, you will get 0. So we are getting this by means of the phasor analysis. Okay. You can use the trigonometric expression also. Cos A minus B you can write as cos A cos B plus sin A sin B. Also trigonometric relation cos A minus B you can write as cos A cos B plus sin A sin B. Okay. So this also can be applied. But the final result is that these three terms will eventually get to 0. So what will be left out? Only 3 cos theta terms are left out. So this you are going to get. Therefore, the instantaneous power is equal to Vm Im by 2 3 times cos theta. Now Vm Im by 2 you can write as what? Vm by root 2 into Im by root 2 into 3 cos theta. So the first thing that you can see here is, first of all, this is a constant value, right? It is constant or not varying with respect to time. Now the final expression you can write as 3 times Vrms IRMS cos theta. Okay. So that means Vrms IRMS cos theta is the average power for one phase. Since you have 3 phases here, you have 3 times of the Vrms IRMS cos theta. Okay. So this is the instantaneous power. Then what will be the average power? When the instantaneous power is constant, the average power will simply be equal to this constant value only. So the average power, the 3-phase average power you can write as 3 into V phase I phase into cos theta. So you can see that this RMS values are of phase values. Okay. RMS of the phase values because we took the phase voltages. Okay. This is for a star connection, but for delta connection also you will get the same result. And what will be the power for single phase? This is going to be V phase I phase cos theta. So that means the 3-phase power we can write as 3 times the single phase power. Okay, so these are the final expressions that you need to remember. So we have derived what the three-phase and the single-phase power in terms of the phase values. Now we want in terms of the line values. Then what will you get? You will simply substitute the expression. Instead of V phase, you will write VL by root 3 or VL, depending on whether it is a star connection or a delta connection, right? So either way you will get the same result. So we will see how that is. If you consider the star connection, then what is the line voltage? It is equal to root 3 times V phase. We are talking about the magnitudes here. And what about the line current? This will be equal to the phase current. So now what will be the three phase power? This is 3 V phase I phase cos theta, which you can write in terms of the line values as VL by root 3 into IL, since I phase is equal to IL. So what will you get? This is theta. So the final expression you are going to get root 3 VLIL cos theta. Now what about for the delta connection? In delta connection, the line voltage is equal to the phase voltage. What about the line current? This is root 3 times the phase current. So the three phase power is going to be 3 V phase I phase cos theta is common. Now here V phase is equal to VL and I phase you will write as IL by root 3 into cos theta. So this is equal to root 3 VL IL cos theta. Once again you got the same expression. Okay, so whether it is star or the delta, in terms of the line values, the expression for three phase power you're going to get the same values. Okay, so once again what are the values that we're talking about here? RMS values. Okay, here also we are talking about the RMS values. Now what about the reactive power? So in the same manner you can get the three phase reactive power is equal to root 3 VL IL sin theta. Similarly here Q3 phase is equal to root 3 VL IL sin theta. Okay, in terms of phase values you will get what? 3 times V phase I phase sin theta. Similarly here. Okay, and finally what is left out? The complex power. This is going to be 3 times V phase I phase conjugate, or in terms of the line values you are going to get root 3 VL bar IL bar conjugate. Here also it is the same thing. 3 times the phase values, I is the conjugate, or root 3 times the line values. And finally the last expression, the last relation is the single phase powers. So the single phase power is equal to three phase power divided by 3. Similarly the reactive power is also divided by 3, and the single phase complex power is also equal to the three phase power divided by 3. Same thing in the delta connection as well.